In this video, I'll be going over how to correctly draw the Lewis structure and then use the Lewis structure to figure out the hybridization, the molecular geometry, the electron geometry of a molecule. My tablet has stopped working, so I'm going to have to find the images of the Lewis structures online to paste into this, but everything else I can type. So normally I would be drawing, but that's not possible right now. So our first compound that we are going to draw has one nitrogen, one oxygen, and one chlorine in it. So we know this is going to be a covalent small molecule because it's only nonmetals, and nitrogen and oxygen and chlorine, those are just individual nonmetals. There are three of them. There are 3 atoms total. And so in order to draw it, we have to figure out a few things. First, we need to figure out how many valence electrons. So if we have one nitrogen atom, it has 5 valence electrons. And then we have one oxygen atom, and it has 6 valence electrons. And then we have one chlorine atom, and it has 7 valence electrons. So total, we have 5 plus 6, which is 11, plus 7, which makes 18. So there are 18 total electrons that we are going to draw in this structure. But how do we draw this structure? Well, we have to figure out what goes in the middle. Since there's 3 atoms, something has to be in the middle. So there are 2 ways that we can look at this. First, which one is the least number of atoms in the structure? Well, there's one of each, so that one does not help. The least electronegative usually goes in the middle. Oxygen is more electronegative than nitrogen and chlorine. So, okay, oxygen will not go in the middle. So now we have to go nitrogen and chlorine. Well, they have the same electronegativity. So how do we figure out which one goes in the middle? What you want to do is you want to use the bonding trends that I went over in class in our notes. And so let me just pull up the bonding trends. Here we go. Okay, here we go, bonding trends. Okay, so one of the easiest ways to draw Lewis structures is to know what kind of bonding trends something has. So carbon likes to form 4 bonds, so something that forms 4 bonds would be in the center with a lot of atoms around it. Oxygen likes 2 bonds, hydrogen only 1, nitrogen likes to form 3 bonds, halogens only like to form 1 when possible. And so of our choices, oxygen, nitrogen, and halogen, chlorine, nitrogen would like to form 3 bonds. So the one that wants to form the most bonds would go in the center. The other way that we can look at this, the most common things that are central atoms are carbon, sulfur, phosphorus, nitrogen, and the metalloids, in that order. And so if carbon is present, it will be a center atom. If sulfur is present, it would be if carbon wasn't. Nitrogen is right here. Nitrogen likes to be in the center with several atoms bonded to it because it likes to form 3 bonds. And so nitrogen would go in the center, and oxygen and chlorine would go around it. So as I mentioned, my drawing tool is not working, so I'm going to have to just paste the structure already drawn into this space, and I'll go over how this is done. So if you use bonding rules, the first thing you do is you write down the atoms. Nitrogen would go in the middle. That means that oxygen and chlorine go around it. You start on the outside and you use the normal bonding rules for oxygen, which is oxygen likes to form 2 bonds and have 4 dots. So 2 bonds, and then 4 dots would be 2 pairs. Then you go to the other outer atom. Chlorine is a halogen. Halogens like to have 1 bond and 6 dots. So that's 3 pairs. Then you go to the middle atom and you look at its bonding trend. Nitrogen likes to form three bonds and have two dots. And so the three bonds were already there. You cannot change the bonds, but you would put two dots. When you're done drawing the molecule, you want to make sure that it has only the number that you had decided that were available for this structure, no more, no less. So you go back and double check. It has 2, 4, 6, 8, 10, 12, 14, 16, 18. So all 18 electrons are shown on this structure. And the way that we go over drawing it, we draw it so that the outer atoms all have zero formal charge, and then the center atom you just add dots until it has a zero formal charge. If you do that, then you will not generate more electrons on paper or lose electrons that you should have drawn if you will always keep in mind the number of bonds and dots that something needs to have a zero formal charge. So to figure out the structure information, you use this valence electron structure over here, this Lewis dot structure. And so we look at the center atom, the number of atoms bonded to the center atom. Well, there's one oxygen and there is one chlorine. So that would be 2 atoms that are bonded to nitrogen. You don't count nitrogen because it's not bonded to itself. The number of lone pairs on the center atom. There is 1 lone pair. So the total here is the number of atoms plus lone pairs. So the total number would be 2 atoms plus 1 lone pair for a total of 3 regions. So I need 3 regions, which means that I need 3 hybrid orbitals. So 3 hybrid orbitals need to be created, and they're created using nitrogen's outermost orbitals. So nitrogen is in period 2, so its outermost energy level is period 2. So nitrogen's going to use 1 s orbital and 2 p orbitals to create 3 sp2 orbitals. So the hybridization, the number of orbitals, that's the number of regions that we went over in the previous video. Those regions are created using nitrogen's orbitals that are in the valence shell. And so nitrogen has s and p orbitals. It only needs 3 of those to come together and create 3 new ones. So if we look here, 3 regions, they create 3 hybrid sp2 orbitals, and the geometry is called trigonal planar, and the angle is about 120 degrees. And so the electron geometry is called trigonal planar. However, since it has 2 atoms and 1 lone pair, the lone pair is invisible. And so the shape of it, it would form a geometry for the electrons of trigonal planar, but one of the orbitals, this orbital here, is kind of invisible. You can't see it. So this is the trigonal planar shape. One of the orbitals goes out and bonds to oxygen, another orbital goes out and bonds to chlorine, and one orbital holds a lone pair. But the lone pair is just mostly empty space. And so because it has 1 lone pair, the molecule, only thing you would see is this molecule here where you have chlorine, nitrogen, and oxygen. And so it would have a bent geometry, just a bent shape, because this upper region you cannot see. The bond angle is about 120 degrees. Okay, polar and nonpolar. So I'm not able to draw the partial charges, but let's see if I can put them. What you do for partial charges is you look and you find the most electronegative atom or atoms that are in the structure. In our structure, oxygen is more electronegative than nitrogen. So the bonds between nitrogen and oxygen, that's a polar bond. Nitrogen and chlorine have almost the same electronegativity, so that's kind of a nonpolar bond. But this bond here would be polar. And so oxygen is more electronegative, and so we would draw a partial negative on oxygen, but I do not think that I'm going to be able to draw that. It'll be in this region, and the partial positive would be at the other end. Let's see if I can get it to go over. It'll be up here above the nitrogen. And if I could use my drawing tool, I would draw it directly on the partial positive would be on the nitrogen. The partial negative is on this oxygen. This is the closest I can get it to be on oxygen. That is because oxygen is more electronegative. What that means is that these electrons that are shared between nitrogen and oxygen, they spend more of their time closer to oxygen. Oxygen has a bigger pull on the electrons than the nitrogen does, because oxygen has more protons in the center. It's going to pull the electrons closer to it. So, is it polar? It is polar. The reason? Anything with a bent geometry is going to be polar. That's the first reason. The second reason is because it has nitrogen in the center with two different elements bonded to it, and nitrogen has a lone pair. All of those make the molecule polar. Sigma bonds and pi bonds. A sigma bond is the first bond between two atoms, and it is created using the hybrid orbitals. And so there are 3 bonds total that are on this structure. The first bond between nitrogen and chlorine, which is only one, that is a sigma bond. And so there's one between nitrogen and chlorine. And then also nitrogen and oxygen, the nitrogen uses one of its hybrid orbitals to bond to oxygen. So there is one that's between nitrogen and oxygen. So that makes a total of 2 sigma bonds. Number of pi bonds. The only time that there is a pi bond present is when there is a double or triple bond in a structure. And there is a double bond right here. The first bond between 2 atoms is created using the hybrid orbital. The second bond is created using an unhybridized orbital. There is one nitrogen-oxygen double bond. And so that means that there's going to be one pi bond. And it's created using p orbital from nitrogen. One of the ones, the only orbital that did not change for nitrogen was a p orbital. Okay. Try to get this all on one page. Okay, the second molecule that we are going to draw together, we're going to look at bromine with 3-fluorine. So the name of this, it's a covalent substance because it's all nonmetals. And to name a covalent binary compound, you use the element name for the first element. So bromine, there's only one of them, so we don't need a prefix. and there are 3 fluorines. So to say there's 3 of them, you say tri, and then we use the anion name. This is not an anion, it's just we use the anion name. So the name of this is bromine trifluoride. To figure out how many valence electrons, we've got 1 bromine, and it has 7 valence electrons, plus we have 3 fluorines, and there's 7 valence electrons on each of those. So that would be a total of 28 valence electrons. So our structure, when we get done drawing it, will have 28 valence electrons. To figure out what goes in the middle, you want to use the rules. And so you want to place the atoms on paper. So we got to draw 1 bromine and 3 fluorines. So one of the ways to figure out what goes in the middle is the element that there's only one of in the formula. For simple molecules, if there's only one of it, it usually is going to be the one in the middle, as long as it is not hydrogen. The most common central atoms are carbon, sulfur, phosphorus, nitrogen, metalloids. We don't have any of those. Hydrogen and fluorine are always outer atoms. Okay, so that gets rid of fluorine as a possible outer atom. Fluorine will be an outer atom. It's not going to be in the center. So we are going to put fluorine on the outside, and we're going to put bromine in the middle. Again, I'm not going to be able to draw it with my drawing tool, so I'm just going to go ahead and paste the structure here, and I'll discuss it. So the first thing you do is you put the bromine in the 3 fluorines, so that you have all of the atoms present. You always start on the outer atom, and for every outer atom you use the rule for that atom to draw it correctly. So fluorine is a halogen, and for a halogen you put 1 bond and 6 dots. So the outer atoms, 1 bond and 6 dots, 1 bond and 6 dots, 1 bond and 6 dots. Bromine is also a halogen, but the 1 bond and 6 dots only applies when it's an outer atom for halogens. If it's a center atom, then you use the rule for center atoms, which is you want to look at the number of bonds it has and see if it has a 0 formal charge. And so it did not, and so just this is how you would look at it. Bromine, it's in group 7, so it has 7 valence electrons, and it needs to have a 0 formal charge. So it has to have the 3 bonds counted, because the number of bonds can't change, and then you have to add a certain number of dots to add up to 7. And so if there's 3 bonds, you would need 4 dots in order for bromine to have a 0 formal charge. And it will be 0 because it's a molecule. Molecules, if possible, the atoms will have a 0 formal charge. So bromine, you put 4 dots. You have to put them in pairs, and you want to put them in a space where you don't already have a bond. So don't worry about this having more electrons than 8, because bromine, its outermost energy level is energy level 4. So it has s, p, d, and f orbitals. So it has plenty of space around it to accommodate more than 8 electrons. So this is the structure, the Lewis dot structure. So you're going to evaluate it. How many atoms are bonded to the central atom? There are 3 fluorine atoms that are bonded to bromine, which is in the center, because we're trying to figure out the hybridization of that center atom. How many lone pairs are on it? This is pairs, not dots. And so there's 2 lone pairs that are bonded to the bromine. The total regions, that would be atoms. There are 3 atoms plus 2 lone pairs for a total of 5 regions. So 5 regions, that's the number of hybrid orbitals that we need. And so we have to count the orbitals that are needed. So if we need 5 hybrid orbitals, Hybrid orbitals are created using the just regular sp and d. And so we're going to use, you always use the s orbital. So we're going to use one of the s orbitals, only the outermost, not the ones in the previous. We're going to use all three of the p orbitals that are in energy level 4 for bromine. That only adds up to 4 orbitals. So we also need one d orbital. And what that creates is it creates 5, and then we combine all those letters together to have this new identity, which would be sp3d. So we're going to create 5 sp3d hybrid orbitals. One s, 3p, 1d orbital. It creates 5 hybrid sp3d orbitals. The geometry for that is called a trigonal bipyramid. Trigonal bipyramid. A trigonal bipyramid shape is a little bit complicated. So let's go down to the geometry here. Here is the trigonal bipyramid geometry here. But for this molecule, only 3 of these spaces are for atoms and 2 of the spaces are for lone pairs. What happens in this situation is the electrons actually want to be further apart because they're not constrained between 2 atoms. They can just roam around. So in the case of a molecule that has 2 lone pairs on the center and 3 atoms, the lone pairs would be in these green spaces here, this one and this one. This is the trigonal planar region. And so there'd be a lone pair in this region, a lone pair in this region, and there'd be a fluorine here and here and here. And so if you just look at the shape in this region here, which would look like this, then that geometry is called a T shape. So not a real complicated terminology at all. Most of the names of the molecular geometries have to do with what you see. There's one, my favorite one is seesaw. So this is the shape. One lone pair and another lone pair. It's in that middle plane. And there's a fluorine in that middle plane, and then there's a fluorine in the upper and lower plane of the trigonal bipyramid shape. So here, here, and here. We also, the lone pairs should be on the fluorines, but again, I can't add them because the tablet is not working. And so this should have the 3 lone pairs on each of the fluorines. This is the geometry around the bromine, and it is just called a T shape. And we're just looking at bond angles. And so here's an angle from this fluorine to this one and this one to this one. So the bond angle is just 90 degrees. This one does not have the 120 because the other things that are in the 120 degree plane are lone pairs, which are not bonds. Is it polar? Yes, it is polar. And the reason it's polar is because it's a T shape. The only way that something can be nonpolar is if every position around the center atom has the same substance, or electrons cancel out themselves and the atoms cancel out themselves. And this does not happen. A T shape is not some kind of symmetrical shape. It's a T shape. The other reason is because there are 2 lone pairs on the bromine. So 1 lone pair, 2 lone pairs, it's going to be a polar geometry. If we put the partial positive and negatives on this, the little partial negative charge should go on the fluorine. So there should be one right here, right here, and on this fluorine, and there should be a partial positive on the bromine. Fluorine is the most electronegative atom there is. If it is polar, it will have partial charges. So partial negative on every fluorine, partial positive on bromine. The number of sigma bonds present. Sigma is the bond that's created using the hybrid orbital. It is the first bond. So if you draw a structure with only single bonds, you only have sigma bonds. So you look over here and we've got 1, 2, 3 bonds, and they're all single. And so there are 3 bromine single bond fluorine. And so there are 3 sigma bonds, because there are 3 separate bromine fluorine single bonds. How many pi bonds? None. Because there are no double or triple bonds. Fluorine does not form double bonds. What orbitals are used to make the pi bonds, or the sigma bonds? The sigma bonds are always created using the hybrid orbitals. And so our hybrid orbitals are sp3d. 3 of the sp3d orbitals. So there's 5 sp3d orbitals total. 2 of these orbitals are lone pairs, and the other 3, here's one of the sp3d orbitals, here's another one, and here's another one. Those are used to create the sigma bonds.